Hello, everyone, and most welcome to an interview with Professor Petter Mostad. And most welcome, Petter, and thank you very much for once more participating in this hot subject, ultra hot.
Well, thank you very much for allowing me to speak my mind. It's quite a bit of fun.
It's a privilege. I'm so lucky. I've been studying science of cognitions since '96, and all of a sudden Bayesian mathematics has completely revolutionized neurology and science of cognition, and it seems to be changing everything at the very core. So of course it's a privilege to have someone who's been looking into these things extensively and give a viewpoint. And I will start out really soft here with a very abstract and philosophical question. And I think that's a good starting ground before it gets too complicated. To cut it short, one used to say that there was no connection between our theories, what we perceived of the world, and the world, so to speak, in itself. So they were two completely separable realms. And it even got a name. It's called Cartesian dualism. And it's actually after a French mathematician who actually visited our country, the only philosopher of rank to come to Sweden early on. And my professor used to say, Sweden hasn't produced any great philosophers, but we have killed one.
Okay, I didn't know this, but I learned it. Yes.
He was exposed to the winter of Sweden, and he had to get up at 4 o'clock in the royal castle in Stockholm to teach Drottning Christina about mathematics and other stuff. But of course, he caught pneumonia, and the rest is sad history. Bayesian mathematics seem to be pointing onto something that we already heard from physics. It's called observer-dependent reality, or that the theory or the priming, what you prefer, is deciding reality. Give us some viewpoints on this, Petter, please.
Yes, well, you cheated, or we cheated, and you sent me this question, and I thought a little bit about it. And of course, well, first of all, it's my viewpoints are very little connected to Bayesian statistics. So what I'm saying is really not something I'm an expert on, but it's my viewpoint. And of course, it's the starting point, and the connection with Bayesian statistics is, of course, that we make a model based on our knowledge of the world, and in that sense, our model of the world becomes observer dependent, right? Because our model is really of the observer's model. So it's observer dependent in that way. And then you could say that, well, does that mean that the reality or a non-observer dependent reality does not exist? And I think that it doesn't, because you can look at this I mean, you can use, or what I do at least, is that I use two perspectives. And one perspective is the where I observe how people think. So if this is sort of perspective A, then this is the model you are making is the model of how people think and learn. And that is based on how their brain works. So when I look at other people or see what they think, then or learn, then the learning process is based on how their brain is working. So in some sense, the brain provides a prior, if we use Bayesian statistics terminology, to the learning process. And then the learning process is kind of like a Bayesian update of that. But you have to have a prior, and that is connected to your brain, basically. And that, in that sense, you have a subjective reality, which is given by your brain. But then, of course, you can also look at this in another perspective, from my perspective, because if I then look at the world, I can see many people doing this kind of learning, and I can also see that I'm doing a similar type of learning. I can compare my own process with those processes of the others. And then it makes sense to hypothesize that we are part of a common reality, which is then not observer dependent. And we are learning about that.
Yes.
Right? Because then that makes sense. And so you have a perspective B where I'm in the center, and then I observe the world, and in that sense, in that perspective, where I start with my own observations, it's not observer. I hypothesize that I observe the real world, and then it's not observer dependent. But and then you combine those two perspectives, so saying that they match together. So you have both a world that is observer dependent, or which is sort of what others learn, and then it's really the same thing. You can see that it's really the same thing as when you use the perspective of me in the center. So for example, in the A perspective, where you have somebody else in the center, free will doesn't necessarily exist. But if you put me in the center, I will say that free will exists, because I can change things. But it's really then two sides of the same thing. So in that, I'm trying to say that my personal opinion is that the world is both observer dependent and non-observer dependent, and these are just two aspects or two perspectives of the same thing. So that's maybe too long answer to this question, but it's
no, not at all.
Mm.
I don't think there is any shorter answer to give. Let me just try and see if I can develop this, if I got it straight. Could one shortly say that since your mind or your thinking is stemming from like observer-dependent reality, since you're constructed from that very same reality? Yeah, okay. That is actually one variety that is combining, as you said, A and B.
Yes.
And it's a rather interesting theory within quantum mechanics as well. So you are stemming from reality. So your, so to speak, subjective, people might say random or coming from nowhere, that is not 100% true, because your structure is stemming from this, has its origin in a way an independent reality. Very interesting. You came to one of the big conclusions within quantum mechanics just thinking this afternoon, Petter. Congratulations.
Okay. Well, it's not a perfect match, but at least, I mean, for me as a statistician, science is about making models, and so you can have different models for different purposes, and in my sense, these two models are then models of the same thing, but using different perspectives, and that's slightly different.
Very good. I often have this problem. I used to, well, I still do, but I've made a lot of lectures about quantum mechanics. And when I say you construct reality yourself, which is, and that's the received way of, so to speak, explaining quantum physics, mechanics, people get scared and they say, well, then everyone can construct their own reality, and that's going to be leading to you're going to become your own bubble, and sounds like magic. It's a second way of responding to that, and some more philosophically inclined are saying, well, that's going to lead to solipsism. Solipsism is the idea that it's just your construction. It's a philosophical strand that would actually Bertrand Russell, the famous British philosopher, really liked it for some while. He changed philosophy many times, but he was a solipsist for a while. There's a famous story that to lighten things up, he had a lecture at Oxford Hall, and one lady, I think it was Lady Ladysmith, she liked the idea and came to Bertrand Russell after the lecture and said, oh, Bertrand Russell, I really do like your theory about solipsism. It's a shame only that there are not more of us.
Yes. Yes. Yeah. Okay. Yeah.
But those objections, I tried to cope with them, and I think your answer is better, that it is a combination, because that will sort of calm them down, get their pulse down to at least 50, 60, so they can think again. Sometimes they put themselves into hysterical mood, and they get like really flustered. But we are stemming from an original outside reality. That's no doubt. It's like it's a combination. I like that. I really like it.
Okay, good.
I think I would borrow that for some of the lectures if it's okay.
Please do.
If you haven't copyrighted it or something.
No. Although, I mean, having these discussions with you makes me explore these. Makes me want to explore these ideas more, because as I understand, the viewers also, they really think these questions are interesting and worth discussing. So I agree.
Yeah, definitely. And it's a bit scary to go into this. I'm not a mathematician myself, and my math is pretty basic. I'm an engineer, and so it's great to have a guide going into this area. Otherwise, it feels a bit scary. Well, on to the next question. It's this is a more or less of a specification of the former question, and once more I would like to bring the battle we mentioned last time between frequentists and Bayesian, what would you say, statistics or Bayesian?
Yeah, Bayesian statistics, yeah, whatever.
And this is the historical development in the line of thinking, in our side of line of thinking. See what we can compare to your side here. But there is how can I explain this? The classical model, or the model of the Newtonian physics, if you oversimplify that, the idea is a bit like there are a lot of, so to speak, objects out there, and they are completely unrelated to each other. So that they can be organized in any way whatsoever. And this was, of course, the dominating absolutely dominating idea of the world and science until at least, I would say, the mid 1910, 1915, something like that. And the idea is all the things you can map them somehow, and to my ear it sounds vaguely what the frequentists are doing. They are not mapping maybe an actual state, but something that goes a bit into the future, like throwing dice or seeing the outcome of different things that you put together. That used to be the case in classical mechanics and Newtonian physics, which led, and this side effect of that was, well, you just have to make more and more observations and more calculations and more, so to speak, almost statistics, and it's pretty much soon or later it's going to be finished. And that became a domineering idea. It influenced a lot of other areas in the beginning of the 20th century. There is an anecdote here when maybe one of the greatest quantum physicists, Max Planck, he spoke to his professor for advice what he was going to do, which line of education should he take, career. And he told them, I'm thinking of physics. And the professor told him, no, that's going to be a finished subject. Don't go into that.
Yeah.
That idea, is it possible that idea was also somewhat similar within the battle between the frequentists and the Bayesian statistics? Can you see some similarities there?
Oh, that's a very difficult question. I haven't thought in that direction before. Because it's also a slight, I mean, in terms of timing, it's not necessarily happening in the same, because I mean, the breakthrough of quantum physics was in the 30s or
20s, 30s, yes. It does no, it doesn't fit in time. No, it doesn't fit.
It doesn't fit so well, but is there a parallel? Maybe. Well, maybe in the sense that you know, in terms of conservatism in science, in some sense, that you believe that things are one thing is the conservatism in how to do science, that you shouldn't, you know, do new ideas, but also I think the thing that we have discussed before about this connection with the observer. I mean, the importance of the observer, which is a fundamental difference in quantum physics, as I understand it, that you put so much, you know, the observer needs to be there in order to make sense, and then it's also the same thing in Bayesian statistics, that you cannot really, I mean, you can formulate it as a mathematical theory, but if you want to apply it, then you need to involve an observer. And this is the same thing, but in terms of, frankly, I really don't know. I mean, you know, so many nice anecdotes about how the history of science has developed, and I don't have any good anecdote in that direction to come with, but maybe there's a connection.
Could it be, you mentioned conservatism, and that is a definite parallel, I'd say.
Yeah,
definitely,
absolutely.
because there is even to this day, if you want to present a paper in quantum mechanics, you have to present it in a classical manner. So it's lingering on. But let me ask you a question. Have you, like, maybe you or someone else from the Bayesian camp, have you met upon frowning faces or sort of lewd comments or something like that?
Not in a while, no.
Not in a while, but it has happened.
No, I guess when I was younger, then it was it's easier when you don't have a title to be frowned on.
Oh yeah, okay,
but yeah, no, I mean, it's I would say that, in all honesty, this debate that we have been talking about is not as fierce, or as I mean, people who were really thinking that the other side were idiots, they are basically gone.
but they used to exist.
Yes.
Wow.
Because you could, I mean, it's possible from a frequentist point of view to say that, Bayesian statistics is pure, is correct statistics, but you add subjectivity. That's all you do. You take perfectly good statistics and you warp it in terms of somebody's personal opinion. And if that's all you do, then it's an argument that goes that way, and then you can say it's all nonsense. You don't want it. You want to rid science of personal opinions. And the other way, you can say that frequentists are just, I mean, people can be rude, but somehow they have become less rude in this field than they used to be, for a change, because in the rest of society people are getting ruder, I guess.
That's absolutely a parallel. So I see the same type of mentality, which we saw and still see to a great extent in physics. Quantum mechanics being frowned on. They try to remake it, at least on the surface. And it's another thing. You just add something that seems unnecessary in retrospect. So they say, oh, quantum mechanics comes to the same conclusion as classical physics. Well, of course they do. But if you start out with classical physics, you won't reach those conclusions. That's the problem.
Okay, yeah.
It's a variety of in looking past things, looking in. It's very easy to be right once it's happened. And then you can always tell, oh, that's how it happened, and that's actually what they do to a greater extent. It's a sort of a degree here in classical mechanics. They look at things afterwards. Where in quantum mechanics, everything is less predictable, and they try to look into the future by not using the past to the same extent. It's not repeatable in the same way. Whereas in classical mechanics, every single thing is bound to repeat itself. For instance, the classical laws, they need to be unchangeable. It's a terror for a classical physicist to even suggest, could it be that maybe the laws of physics being slightly different? And that they go in directly into a tantrum, the direct direction. Well, very good. I sprang this question on you, Petter, but you did a very good job. That enlightened us a lot. That's odd that the same thing is going on there. Wow. And now on to a quite much lighter question, and it does have some relation to things that we discussed before. One of the reasons a lot of people sends question to me and are interested in these things when I talk about it is that now Bayesian mathematics and statistics has entered into neurology and science of cognition. And one famous name there is, oh my God, he's Hungarian, György Buzsaki. I hope I got that right. And he says that the brain is a sort of predictor or random predictor. Let's take this question apart. I start with this random predictor, as sometimes it's called within neurology. Do you have something equivalent in Bayesian statistic, that randomness? Could it be the prior that you sort of throw in, or?
Well, I mean, any prediction in Bayesian statistics is stochastic.
Oh,
right. So if you predict something, it's really about a probability that something will happen, a probability distribution, or if you have separate outcomes, you have probabilities. So you can say that if you make an actual prediction, then with those probabilities, you make those different predictions. So I would say that that's best parallel, and maybe that's what he meant.
Yeah, it sounds like it. Thanks. Great. Yeah, definitely. Sort of a random processor of sorts. Of course, it has also in neurology caused an enormous turmoil. And thank God this György Buzsaki is a very calm fella. I really like his way of lecturing. He's speaking this slow Hungarian accent. Bit monotonous, but still it gives a lot of confidence. And once asked, he takes some time to answer the question. And that there are varieties of this. There is a Swiss professor called Pfeifer, Dr. Pfeifer, and he did almost even more. The Brain Inside Out is the famous book by György Buzsaki for the public, for layman. I recommend it. But he did Inside Outside, and put the, so to say, the brain, which is the inside, he put it into the body. So one can go into YouTube, for instance, and see his mechanical devices that doesn't have a CPU or any central processor or any RAM or anything of that. It's all in the outside. So they are constructed in a way so that construction gives them a movement. And this movement is very close to the randomness or the guess about reality. And the odd thing is, this is so fascinating. When these things move about, they learn. It's like in the movement, they threw something out, and slowly the movements change, and you can actually see some sort of progress. And it's so odd. It's like maybe there's a second question here. Maybe it's Bayesian statistic mathematics is closer to, how can you say, the workings of the world, or how things go about. What do you think about that?
Yeah. I mean, Bayesian statistics. I really think that people who are listening to this and want to learn about Bayesian statistics should look into the basic mathematics of this, because the basic mathematics is really fairly simple, and when you do that, then you will see that it's really not that. I mean, it's very simple, and that means that this simple idea can be reflected in so many ways, right? Because it's not a complex way of computing things. It's a very simple idea where you sort of just throw away the possibilities that are no longer possible because of your data, and then what remains is the distribution, the probability distribution over what you want to predict. And then the Bayesian statistics is just the mathematics of how to do this in very complex systems. And of course, I mean, very complex systems that have this feature where you simply have a lot of possible, say, movements or possible outcomes, and then some of them are, for some reason, discouraged, either because they are, just made impossible, or because they are somehow discouraged by this mechanism or
okay. Wow.
If these mechanisms, some movements are basically not good or not happening, then you have the same effect as this very simple Bayesian updating mechanism, where you basically end up doing the movements that are not discouraged or are allowed. And that's simply Bayesian learning.
Wow.
And it's a learning in another way also. So I really think there can be a parallel, but to see that parallel, it's very helpful to just think of this Bayesian learning as a conditioning where you remove options that are no longer viable for some reason in this particular setting that you're looking at. So I mean, and this also illustrates how Bayesian statistics is very close to evolution.
Oh,
Because
yeah.
evolution is also about taking away options which are not viable or not helpful for the organism, and then basically the organism evolves by selecting among the remaining options. It's exactly the same mechanism, and that's what evolution is about, really.
So learning could in itself be Bayesian.
Yes.
Yeah, okay.
Yeah.
Well, that definitely goes into the direction of György Buzsaki et al. And this doctor with his mechanoid devices. They're absolutely beautiful. I'll see if I can find his YouTube clip and attach it to the description of this. And it's just fantastic. It's like they are rather clumsy in the beginning. You give it a couple of days and they start moving more graciously. They start discovering each other. How that works, I have no idea. I think he doesn't even know himself. I don't know. It's just me chancing. But they seem to be able to do fantastic things. And after a while, even some other devices, not all of them, can climb steps, both first down and then up. And movement could have this, and as you said, simple. It's actually simple in
so the basic mechanism is probably very simple, that you sort of disallow or discourage at least the things that don't work or the movements that are problematic in some sense, and then it learns.
Wow. No wonder they fell for the Bayesian mathematics. I start to understand it better. There's an incredibly interesting development within neurology and brain research, and that this is now beginning to hit AI, artificial intelligence. The old idea was, when I began, it was, artificial intelligence. The only thing, we need a machine that gathers all the information in the world, and then you have intelligence.
I agree. I mean, the latest development in AI are very much about, I would say that they are most easily described using the concepts of evolution. I mean, you put systems into limitations that forces them to do what forces them in the direction where you want them to go. And as we just discussed, this is also, I mean, it's the same really underlying idea in evolution and in Bayesian statistics.
Wow, even more interesting. Wow. And it was great, Peter. Thank you very much.
Well, thank you.
I think we settled for these three questions. It's mind-numbing, incredibly informative as usual. Great clarification. It's like The
Thank
subject
you
is
for a
opening
very,
up.
very nice discussion.
And we see what happens with the audience here now, but I think they have a lot now. That's really great. Thank you. And I'll contact you when the questions start popping up and preparing.
Okay. Okay. Well,
Thank
thank you.
Thank you very much, Petter Mostad from Gothenburg. Have a very pleasant evening, everyone who's listening. And see you next. Bye-bye.
Bye-bye.
Bye, Petter.